Hey, science students. Hey, welcome back to your latest, I shouldn't say latest since they're almost all, I've already got them all recorded before the school year started, but your next, how about the word next? Video lecture. This is part two of our macromolecules. But again, welcome. Thank you for opening this up. Thank you for being a part of all this. And as you can see on the screen, a bunch of stuff, and you may be going, which I can understand. But man, some awesome stuff. I mean, awesome stuff. And not just awesome, but just super, super important to what happens. I use the word daily, but that's not even right. Almost, every minute, every second, these things are hard at work, making sure that everything goes on properly. Our two topics today, proteins and nucleic acid. I mean, you can't get any more important than those two groups. Uh, Nucleic acid, DNA, RNA, you're probably pretty familiar with that. Proteins, hopefully, if you are a high school student currently, that from your EOC days, you looked at these pretty strongly, but we certainly will today during this time together. If you are a Crowder student, hopefully your graduation is fairly recent. And again, you would have had hopefully your EOC class. And if you did take it dual credit, which is probably not the case since you're here with me today, but if you're an A&P student at Crowder, maybe you did take dual credit and you've had a second look at that. For the rest of us, hey, we'll just learn this together. But man, incredible stuff, fun stuff to talk about, interesting stuff to talk about, great stuff to talk about. It's just fantastic stuff. Love this stuff, as I've already said too many times, probably. Uh, but just a good look at how your body operates on a daily fashion to get the stuff done that needs to get done. I mean, it is just a great couple of topics that we've got going today. So, with that, let's get the welcome out of the way again, because this is part two of the macromolecules. So, it's the same group as last time, which for some of you might have just been last hour because we're watching these back to back. But hey, welcome to the Nevada High School students, dual credit class, A&P class. Thank you for being a part of this. Welcome to the Crowder students, Bio 1, A&P 1. Welcome to you as well. And hopefully everything is going well with you and that you are safe and sound. And again, as always, take advantage of this format. If you get sleepy, get tired, get bored, something comes up, phone call comes in, whatever, message, and you got to deal with it, just hit the pause button and then come back to it when you can, when you need to. As your own schedule determines. You may have work, maybe the weekend, maybe Tuesday night, maybe Thursday morning. Who knows? Just take advantage of this. Do what you got to do, but make sure you get everything taken care of. As always, with the amount of notes, that's kind of determined by what your school is. If you're a Crowder student, hey, it's college. You're on your own to get the information. The more you write down, the more drawings that you participate in, the better informed you will be, and the better you will do. Once we get into the classroom. But we will spend plenty of time building these with the chemistry building blocks and talking about this stuff. And we will just have a great time. Same in with the Nevada High School students, your grade is on the line, so be sure that you take care of the notes and get everything written down. You can work at your own pace, as we know, as we've said. So just take the time to get through this. Again, hopefully, I will be able to keep this within an hour. I did pretty good last one. I think it's like 52 minutes, so I was real good there. Uh, and this one probably will be maybe even a little shorter than that, but don't hold me to that, because even though it's big stuff, exciting stuff, we're probably going to get through this fairly quickly, because one, we don't have all the background information to go over, the dehydration synthesis, the hydrolysis, monomers, polymers, that kind of stuff. So, but we will be talking about those things. I mean, you can see the word dehydration synthesis right there. We got the word monomers right there. So that stuff will certainly be a part of our discussion today. So with that, welcome. Thank you. Hope everything is going good where you are. And with that, we will get started. So let's start here. Let me zoom in a little bit, bring this kind of closer. We don't need to see all this right off the bat. Let me bring this down and get me a pen. And I really enjoyed that blue yesterday, but you can't do the same thing all the time. So let's see what else I got in here. Let's go over here. And hey, you've seen this a couple of times. If you ever have a color preference, just let me know, and we will pull up your favorite color. Let's go. How about a nice green today? Nice green. And what new pattern do I have? Yeah, that's good for right there. All right. So again, here we go. Welcome, and let's get started. We're going to start all the way over here. Now, the first thing we want to mention about proteins. Proteins are the worker bees of the cells. If there is a job to be done, a protein of some fashion is doing that job. And I mean anything. If it's a job to be done, if it's a chore, if it's a task, a protein of some type is getting that done. So super, super important molecules, the proteins are. And that's why they have such a long list of functions, because they do all the jobs. Okay, if you could think about a city, think about Nevada, think about a city that you live in, think of all the tasks that have to be done in that city, or that are done within that city, not just the ones that has to be done to make sure the city operates, the police, the fire, the city hall, whatever. But I mean trash. I'm talking about construction, anything. Think about all those people that doing those jobs in the life of the cell. Those would all be some type of protein. So that's kind of the mindset to think about. All right, so whether it's defense, transport, support, motion, regulation, storage, whatever, okay, a protein is doing the job. And just to emphasize particular jobs and proteins, again, these are just examples. We'll start here. This particular situation here is an enzyme, and this enzymes are designed to increase the chemical reaction that occurs within a molecule or for a molecule. You can't read the writing; it's pretty fuzzy if I get any bigger, but we can certainly see the image. So in this particular job, this particular protein, which is an enzyme, is helping to break down this molecule. It's actually, and you can see that it's converting it first from one form to another. So that's a job. Another job that proteins have is to help with, and now I'm right here, help with, you know what, I like this green too, help with getting things in and out of the cell. This scene here, this is the, as you can see here, this is the plasma membrane. Okay, and these proteins, these green globs here, those are proteins. They are helping to allow things to get in and out of the cell. And when we do chapter 5 I should say, if you're a bio student, when we do chapter 5, the plasma membrane, we will talk about this kind of stuff um, to death. I mean, you get tired of hearing about all these great proteins and all the jobs that they're doing. And this is also the plasma membrane. This is an expanded view, obviously. And again, all these blobs here, these are proteins helping things to get in and out of the cell. So let me close this and kind of bring this. I don't want that. I don't want to get that line in the picture, nor do I want to pull up the eraser and slow the education train down. So we're gonna talk right here. This is where we are. This is a diagram of the structure of a protein. Now, proteins, because they do have so many different functions, their structure is, you would think it'd be a lot different, protein to protein, based on what they have to do. That's not quite the way it is. They are all structured essentially the same, and the difference between each of them is what determines what their function is going to be. And I'll talk about that, but that's box 5, or this R box out here. But let's start first. I'm going to go down this list and kind of show you on this diagram where these things are. So let's start with the central carbon atom. That's going to be right in here. So I'm going to put a 1 right there. That's the central carbon atom. That kind of makes sense because it's in the middle, and kind of the setting the structure for everything else. Okay, the amino group, which is labeled right up here. So this is going to be number 2. You can also see because it's got that nitrogen right there. Now, what that does is kind of sets the stage for what amino acid will be formed later on. But that's part 2 of the structure. You got that amino group, and again, it's always 2 hydrogens and a nitrogen on that side of the overall molecule. Number 3, and again, that's labeled right there, the carboxyl group. So let me put a 3 here. And that word carboxyl refers to when you have a carbon and 2 oxygens with that hydrogen, that's a carboxyl group. So anytime in a chemistry setting you see that word carboxyl, you know you got a carbon with 2 oxygens and a hydrogen off of one of the oxygens. Okay, so that's part 4. Now, part 3, part 4 is going to be this little hydrogen sitting right there by himself. Okay, so you're always going to have that. So those 4 parts are always the same, regardless of what protein it is. Those are always the same. Now we're going to talk about number 5 right here, the R box. Okay, I'm going to put a 5 right here. This R, what this R represents is for each of the individual proteins, there's going to be a molecule there, and that molecule determines or allows, however you want to say it, what its function or job is going to be. In other words, whatever particular molecule gets put there, that's what job it does. And it'll make more sense when we get up to here and we look at those different R groups. But it can be a huge variety of things, which leads to all the different tasks. So let me say it in a different way. If the protein is designed to be a defense protein, then it's going to have the R group there that allows it to do that. If it's supposed to be a motion protein, in other words, transport, and I shouldn't say transport, but some kind of movement or motion, then it will have a different R group there, and it will allow it to do that protein, that function. If it's supposed to be storage, again, it'll have a different R group there, which will allow it to be a storage protein. So let's close this out and let's bring this kind of more into view. And I'm going to go a little bit bigger here so we kind of see all this stuff pretty easily. So again, we're going to be talking about this. Oh, didn't mean to do that. In main tray, we're going to be talking about this box right here. Okay, each of these, and you can see the names. Maybe kind of hard to see, especially if you're on your phone. But the names are there, and you will. And what you can see is that everything is the same. That's the carboxyl group. That's that individual hydrogen. They just have it in a different spot than what our other diagram had at. So all this stuff is the same. The hydrogens and the nitrogens, all that is the same. What's different is the shaded blue boxes. That's that R group. And having each of those R groups as a different, or the variety, is what leads to the task that particular protein would do. So you can see all the different variations. Some have just a single hydrogen. Here you've got a carbon with 3 hydrogens. Here you got these big carbon rings that we talked about yesterday. So that's the idea of the variety and the R groups. And when you have that variety, or one of the benefits of having that variety, is the fact that you can have different amino acids. So based on what R group is there, it forms an amino acid as that protein. All right, and so these R groups, some of the other varieties can be polar, it can be non-polar, it can be charged. So lots of variety there as well. So let me close this and scroll this down and over just a little bit so we can get all those words in there so you can see everything. And get my pen back up here. All right, now this box here goes with this information down here. So you're thinking that this is beside it, so that must go there. But no, we are going to talk about this stuff here. This is just simply notes or ideas about proteins. That's what we're going to talk about now. Okay, so we talked about monomers and stuff, and a protein is a long chain of amino acids. So amino acids would be the monomer, proteins are the polymers. And whether it's from just growing up or information or nutrition or health class or whatever, 20 amino acids, 10 essential ones. And these polymers, these proteins can be shorter. They can be super long, as you can see, over 5,000. But each amino acid, as it's connected, it's called a peptide bond. And this isn't a bond like ionic bond or covalent bond or hydrogen bond. It's just a connection between two amino acids. And so it's called a peptide bond. Now, other fun stuff, as we do come over here and talk about this box and this information, dehydration synthesis. Now, again, in this box here, this is before and this is after. So you've got these two amino acids, and you can see we've got our OH here, our OH and our H. Now, this isn't the typical OH stuff that we'd seen yesterday with the carbohydrates. This is just simply one has an OH, and because they have these alternating ones, this molecule, its OH is over here, but does have this H here, does have an OH here. So obviously you can see what's going to happen. This water molecule is going to leave, and then essentially the N and the C become connected together, and you can see that right here. So that's a peptide bond. So when you see the word peptide bond, it's referring to amino acids being joined together to form a chain, which forms a protein. Excuse me. All right, and it happens through dehydration synthesis, just like we talked about yesterday. And then you can see here that the carboxyl group of one amino acid is linked to the amino group of the other amino acid. So if we close this and go back over to our structure here, essentially what happens is that, if you can imagine, this carboxyl group is going to attach to this amino acid group or amino group of the next amino acid. All right, so let's bring this back over. And now I think we are, let me back out, see where we are. I think we're ready to talk about, the protein's structures. Yep. And I think this is our last topic in the protein discussion. So let's go a little bit bigger here. Now, all right, so we built this long chain of amino acids. So we built this long chain of amino acids, and we're going to make a protein. Now, similar to DNA, you can think about DNA, you know the process of replication, transcription, translation. But you also know that, or hopefully you know that, your DNA strands are really long. Okay, really long, but they've got to be folded in such a way that they can fit into a cell, which obviously is microscopic. And not just fit into the cell, they've got to go into the DNA. To the nucleus of a cell. So just a small compartment of the cell. So you got to have some serious folding. Now, if you can imagine, let's think of it like this. At our house, when we go on a trip, we don't go on too many just long trips like we're going to be gone for 4 or 5 days, but we do a lot of weekend trips. You go somewhere, go over to Memphis, go to St. Louis, go to Fayetteville, whatever. So we'll do some Friday nights, Sunday night stuff. And so we have to pack for a couple of days. Now at our house, I can get everything into a nice gym bag, nice duffel bag, where somebody else, I'm not going to mention any names, but she might need 3 or 4 bags. It's because she just puts things in there. But if you take the clothing, the shirts and the socks and everything, and you fold them up in a very nice, tight pattern or compartments, you can get a lot of stuff into a small area. And that's what happens with your DNA. And that's what we're going to talk about now. That's what happens with your proteins. Because these proteins, as we saw, can be very long. If you got a string of amino acids that's 5,000 long, that's a long chain. But your body is so efficient at getting stuff done and doing things, and your proteins are structured in such a way, folded, if you want to, in such a way that they're able to fit inside of wherever they need to be, whatever cell they need to be. And that's a 4, as you can see here. Get my pen up and going here. That's a 4-step process to get that done. So, number one, primary, the first part of this process is just simply the building of a protein. You get these strands of amino acids, and here are various amino acids. And if you're a bio student, when we talk about DNA as far as a chapter or a unit, however you want to say it, we'll talk more about amino acids and what they are and what they mean and what they do and their connection with building of a protein. When we do replication, transcription, translation, and we talk about RNA, we'll talk about that a bunch. But for the A&P people, this is just simply a process discussion. And so you build this protein. Okay, you've got the amino acids, peptide bonds here, and that's what the arrows are showing you. That's where the peptide bond is. That's why you keep seeing these NH, 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 and then the bond. Okay, so that's part one, just building of the protein itself. Okay, and so now we're going to come over here and talk about secondary structures. So this would be part two of our folding process. Now some cool things happen here. Okay, the first step in getting these into a tight compartment. Okay, the A helix and the B pleated sheets. So it's kind of color coded here to give you some kind of three-dimensional look on a two-dimensional plane. So we're going to do the best we can here. But what happens, you can almost think of it as accordion style folds. I know an accordion. I don't even know if that's a relevant instrument anymore. You may be thinking, well, I know exactly what an accordion is. We're kind of our cultural history has that's been a part of it. Or you may be thinking, I don't even know what you're talking about. You'll have to just look it up. And you can kind of see it over here as well. But just these folds, okay, which allow it. If you can think, if you took a strip of paper, and begin making 1-inch folds, then you could really compress that piece of paper, that strip of paper down to where you could fold it onto itself to where it'd be super thin. Okay, so it'd go from maybe a 7-inch strip of paper, and if you did 1-inch folds, you could go down to where you could stack them up on top of each other to where it'd be less than 1/4 of an inch tall. And so you just reduce the space that strip of paper needs. That's what's going on here. So you make these folds. That's the B pleated sheets. You can see right there. And in each of these folds, then it's also spiraled. Okay, so it's spiraled to really condense the amount of space that it takes up. And based on what amino acid is, some amino acids form the A helix, others form the B pleated sheet, but they kind of got to work in conjunction with each other to get all this job done. So the secondary structure, you get the folds, you get the spirals, and to do that, when you do that, you can get that really thing condensed down as far as space that it needs to take up. Again, excuse me. So now these pictures kind of work in conjunction. So, but they're too big to see this on the screen at the same time. So I'm going to go this direction and talk about 3 and 4, but then we'll come back and look at this picture because this has all 4 of them in one spot, and then we can really tie it all together. No pun intended. All right, so let me move over here to 3 and 4. Okay, and bring the pen back up. Okay, so here we are, tertiary, and of course this word and this word along with primary and secondary. These are kind of geometry type words. This would be 3 and this would be 4. Okay, so now that I've got them folded and spiraled, okay, in part 2, now we're going to condense them down even further by having, and I'm going to make a connection there, and I'm going to make an emphasis there. Okay, so we're going to create these links or these bonds or these connection points designed to kind of draw them in. So if you can imagine, sometimes I use garden hose, rope, whatever you want to use, but sometimes on a garden hose, people just loop it around those garden hose brackets that hold it on the side of a house or wherever. But you can imagine if you took a rope, okay, and kind of made little loops with it, but you kept your hand around the middle. So the rope is sticking at the top, sticking at the bottom, but you got your hand in the middle, or you can even tie the middle up once you've put the rope kind of all in one. You can also see this can be in like a crochet yarn that's still in the package, where it's these long loops, and in the middle is where the wrap is, the glued piece of paper to kind of hold it together. We make these loops, and we connect these points with these disulfide links, kind of anchoring points designed to kind of fashion it to where it's kind of looped together, held together as a way, again, to try to condense it down even further. When we're in class, I'll demonstrate this with some yarn or some kind of material to where you can see me bring it together. We'll fold up sheets of paper, we'll spiral them, we'll do all that stuff to kind of get you that mental image of what's happening. Now, the first 3 steps are unique in the fact that we're just working with one protein strand. Part 4 here, as you can see, and they color code them like this green. This is one. This is another over here, another over here, and another over here. It looks like I need to go over a little bit more so you can see the rest of those words. Okay, so now we're joining the protein that we folded and structured in parts 1, 2, and 3 with others that have had the same thing done with them. So quaternary, now you've got the individual that we worked on or was showcasing connected to others as well. In this case, you would see 4 different proteins. So part 4 is simply the joining of the folded protein with other folded proteins to make this big structure, quaternary structure. So that's the 4 parts of folding or structuring a protein so it can be compartmentalized in a very small area. Okay, close the ink tray, go back over here as promised, and we'll get this right in the middle here, and then we can zoom in on it. And we can go a little bit bigger. Yeah, there we go. All right, and you can actually read some of the words too. So this is obviously part 1. Main tray. This is part 1, 2, 3, and 4. So we build the long chain. We do the B pleated sheets and the alpha helix. We then make those loops and connect them to each other, and you can kind of see the previous step in there. And then 4, joining them with others to get them compartmentalized. Okay, so I'm going to zoom out just to make sure, but I think that ends our that carbohydrate stuff off our screen. I think that kind of ends our discussion on proteins. Yeah, we've been through all of that. So with that, we'll begin talking about nucleic acid. And nucleic acid has a lot It's still super important, but there, as you can see, it's just all this stuff. And you can do that. It's all this stuff right in here. So not nearly as much stuff going on. And hopefully you see that and you're going, oh yeah, I remember that from EOC days. I love doing that stuff. Excuse me. So let's get in here and get started. Close this. We can adjust our spacing here. And good. We'll get everything on the screen and start talking about it. So we're going to start obviously right here, nucleic acid. Now, the nucleic acid, monomer, polymer stuff, the individual nucleotides. Okay, that is the monomer, and that is right over here, which we're going to talk about. Okay, and then of course the polymer is a big collection of those. Okay, a big collection of those. So monomer here, I'll put an M right here, and then this is what a polymer would look like. Okay, the big old double helix chain there. All right, so let's break down this information here. Okay, so when the structure of a nucleotide, which is what this is, so this word here, this is what we're looking at right over here, nucleotide. You got a sugar, a phosphate, and a nitrogenous base. Okay, so let's identify these parts. Down here, this is where your sugar is going to be. Okay, obviously there's a phosphate right there, so that's easy to identify. That's the phosphate group, and of course in that leaves, and you can see all these ends. So that's obviously your, I'm just going to put an NB for space, but recognize that that is the nitrogenous base. All right, so you have those three components to build a nucleotide, and of course nucleotides are always the same. Okay, always the same as far as the structure. All right, so our next part to talk about is, now we're talking nucleic acids in general. Okay, but you should know, or hopefully you know, that there are two types. There's the DNA, but there's also the RNA. So we're going to talk over here now. So these are always the same. You got the phosphate group, you got the nitrogenous base, and you've got the sugar. Now, but where the variety is with the sugar and the nitrogenous base. Okay, what the sugar can be one of two, and these are your two choices here. It can be deoxyribose, or it can be ribose, and you can see the only difference between the two is this hydrogen right here. No, I'm sorry, not the hydrogen, the oxygen. Scratch that, because there's the hydrogen there. I just went bottom of that list. That's my error. It's that oxygen right there. So if it's deoxyribose is the sugar, then you've got a DNA strand or a DNA component. If it's ribose in that sugar spot, then you've got RNA component. The other variety is with the nitrogenous base. Okay, that's what determines, probably the best way of saying this is, hopefully you remember the A, T, C, G stuff. Okay, and then I'll put a U down here in case we're RNA. But this section here is what determines if it's an A, T, C, G, or U component. Okay, so that's the idea of the structure of a nucleic acid. Phosphate group, sugar, which has a option of 2, and then the nitrogenous base has an option of 4, regardless of what sugar it is, but it's either ATCG or AUCG if it's RNA. Okay, but again, hopefully this is all old stuff, review, all that good stuff. Hopefully your EOC class, your dual credit class, if you had that. If you took chemistry in high school, you might have talked about it there as well. Okay, our next thing to talk about is we're going to go right here, talk about this stuff. Now we're going to be talking about DNA. Okay, this is DNA information. Now, on DNA, as I just mentioned, if we're talking about the nitrogenous base, okay, we've got 4 options. It can be an A, it can be a T, it can be a C, or it can be a G. And if you're a bio student, when we get to the DNA section, we'll really hammer the base pairs. But we're going to ignore this part. That really doesn't need to be there. But we're going to talk about these right here. So A pairs with T, and C pairs with G. And where that comes into play is when you're replicating the DNA strand. So, and that takes a lot of work. So if it takes a lot of work, the thing to think about is the proteins that get all that done. But when a DNA strand is copied, and again, once we talk DNA as a unit, we will go over this way too much, probably in your mind once we get there. But when a DNA strand is being copied, one protein reads the original strand, and other proteins collect the needed matching pair, and that's how the DNA strand is copied or duplicated. So it is an exact copy. It's just obviously going to be in reverse because if I'm reading CGT, then I'm going to be making the opposite. But at the other end, that's where, anyway, you'll see it. So let's just practice this, or let's just talk about this. So on the original strand, there's a T, then the protein polymerase is going to put an A there. T, so it's going to put an A there. If it's an A, it's then going to put a T. If it's a C, it's going to put a G there, and a C, and you kind of get the idea. A and a G. So like that. And then that forms codons, and that's how the amino acids are determined. But again, we'll talk about all that in the DNA section. And let me blow this up a little bit here. I marked on it. So I marked on it, so it ain't going to let me expand a bit. So we'll just talk to it as is. We're going to talk here. What we talked about here, this is an example of it. So if we look at, it's running this way. I was looking at it sideways one. But here you can see that in the connection, you have an A, and so it's partnered with a T. And here the same thing. We've got cytosine and guanine, C and G. Those are paired together. So that's the complementary base pairs. But again, just information here. But once we get to those units, if that's on your chore list, then we'll talk about those in great depth. I'll just say it at that. So our last part, we're down here. Now we're talking RNA. Okay, so the couple things that switch. Now our sugar is ribose, instead of deoxyribose, we'll cross that out. And instead of using the T or thymine, we're going to use uracil. So now our base pairs are A and U and C and G. So that's the differences with and when we reading or copying RNA or duplicating RNA, those base pairings like that. And RNA is super important because it does a lot of things. It determines what proteins we're going to make, all that kind of stuff. But again, we'll talk about all that at the appropriate units. So I think, let me go out here. I think that's going to be the material right there. Yeah, because we covered all of our stuff here. So there we go. That's our proteins. That's our nucleic acid discussion. And the bittersweet part of this is we have, because of the beginning of the semester and the information, the scientific method, the chemistry, the macromolecules, all that stuff, everybody studied or talked about, or it's on your list of chapters to cover. But unfortunately, now is when our classes will split. The A&P people will go and do their stuff. The bio people will go and do their stuff. So this will be the last time that we get to be all together. So I'll certainly miss that as far as kind of the mentor. I know we're not actually all together. I understand that. This would be a pretty crowded office if we were all together. That'd be at least 150 people, so we don't want that. I certainly don't have enough chairs for everybody. But with that, we will start to say goodbye. And again, thank you very much for pulling this up. And hopefully you learned some things, enjoyed some things, saw some things that maybe you didn't know. But again, but I do hope that it was a big review for most of you, which will make it easier for you to digest the material and so on and so forth. So until next time, let's see. A&P people, I think you go right into. I don't know. Maybe I think you probably go into tissues. That introductory structure. But bio people, I do know what you do because I taught this stuff forever. The A&P side new to me. But you guys will be going into chapter 4, which is the organelles, the internal cell stuff. So that's always exciting, and again, but hopefully a review as well. So nucleus, nucleolus, all that stuff, ribosomes, all that good stuff. So with that, we will say goodbye until next time.